I would like to start from the energy challenge. Energy challenge means that every year the energy consumption of the human population is increasing in the world. You see this graph, the power in terawatts. Tera means 10 times 12. Used in the world as a function of the years, and you see that this is the total consumption which goes up, and here you see by different countries how it goes up. You see this tendency is increasing, and now we are at about 20 terawatt energy produced in the world and used. Especially big growth is in developing countries, which are industries coming up. In China, India, Africa is coming more and more. So people need more and more energy, and not only producing energy, but also this energy should be distributed to the consumer. And here where the phenomena of superconductivity is very important, because as you know, you need to bring electricity, for example, which is produced from the power plant to the consumer by electric cables. And these electric cables have limited capacity to conduct current. So, probably most of you don't know what is superconductivity. I will explain it quickly. But before this, probably you know what is conductivity. Yes? We know that electric cables consist of the metal, and they can conduct electricity. This we know. Okay. Now, this is the map of United States. A real map is taken, the photograph is taken during the night by satellite. And you see here bright points here. It means these are big cities which are mostly illuminated. So you see where the most population is, the east coast and west coast. And here is a black area. This black area corresponds to the New York City and surrounding. Why this is black? Because in 2003 there was a so-called northeast blackout, when suddenly there was the electric system breakdown. The cables could not conduct the current, and there was a shortcut of electricity. This is called blackout. So it means that we are already on the limit of the existing cables to conduct the electricity we need. So it would be very good to have the cables which could conduct more electric current than we at present. And this can be done by superconductivity. But before we go to superconductivity, let's recall what is the electric current. Electric current we can conduct in metals, and why metals are good conductors? Because in metals we have free electrons which can move freely and conduct electricity. What is the electric current? Electric current is ordered motion of electrons. So if we have such a cable, and these are, let's say, electrons, all electrons move in one direction. This is electric current, like water is flowing in one direction. Okay? But life is tough for free electrons. Free electrons cannot move freely. They experience resistance when they move. Why they experience resistance? Because they are colliding with each other, they are colliding with other atoms. And for example, if these white points are electrons, they move from left to right, but they are atoms which are fluctuating, oscillating in the metal, and they collide with electrons, and the electrons lose energy, they lose the velocity. So this is like a friction. When you slide on the floor, you will stop, and your shoes will get warm. Like this, when you pass electric current in the conductor, it gets warm and finally hot, and it can melt finally, okay, if you pass a very large current. So how can we avoid this? So the reason is resistivity. This is friction in metals. So this is called resistivity. Like you roll the ball, and after some time this will stop because of the friction. So let's decrease this friction, this resistivity. How one can decrease the resistivity? Different metals have different resistivity, and the best conductor is copper. That's why copper is used everywhere in cables. So another way to decrease resistivity is to cool the metal, to decrease its temperature. It is known that if you cool the metal, for example, here it's shown cold wire, this warm wire. In warm wire, you see the vibration of atoms are much less, and the electrons can move with faster. It means resistivity is decreasing. Indeed, this is the case. If you plot a graph, resistivity versus temperature, resistivity is decreasing with decreasing temperature. So one way is to cool conductor. Okay, but how far we can go with this down with the resistivity? So there is a question: how much we can cool the conductor? Where is the limit? And here I should remind you temperature. What is the temperature? Temperature, if you have atoms, let's say gas, these atoms in this room, they are moving, and higher is the temperature, faster they are moving. So we can say that temperature is a measure of the velocity of the atoms. So hot means in physics a body where the atoms move fast, and cool means they move slow. So if we continue this analogy, then hot means fast, slow, and finally there should be some temperature where the motion stops at all. Yes, because velocity is decreasing with decreasing temperature. And finally, we should reach temperature where the atom's motion will stop, and indeed such a temperature exists. And this is called absolute zero. Absolute zero. At absolute zero, every motion, atomic motion, is stopping, and it's not possible to reach a lower temperature. It makes no sense. Yeah, this is the limit. So, what is this temperature? How much it is? For this, we should recall that there are two main scales of temperature measurement: Celsius, which we use everyday life, and Kelvin. Kelvin is used in physics. For example, to convert between Celsius and Kelvin is easy. For example, 100 Celsius boiling water temperature is 373.15 Kelvin. So it is a difference about 273. Yes? So if you have temperature in Celsius, you can convert it to Kelvin by adding 273. Similarly, if you have at zero temperature, it's ice forming. Yes, in Celsius scale, this is in Kelvin scale. Sorry, this is 273. And finally, absolute zero temperature in Kelvin scale corresponds to minus 273 Celsius. So the absolute zero in Celsius is minus 273. This is the lowest temperature in nature. You cannot have minus 300 or minus 500. It makes no sense. It's Celsius. You can have plus 1,000, even million, but minus you can have only minus 273. Okay?
Also in the universe?
In the universe, yes. So this is actually the scale, temperature scale in kelvins. This is absolute zero here. And actually, you asked about universe. In open space, in cosmos, temperature is very close to zero, but it's not zero. It is 2.7 Kelvin. It's very cold. Cosmos is very cold, but it's not zero. So from this up, we can go up to the room temperature. Yes, different temperatures are shown here. So to get used to the Kelvin scale, I use this scheme. So here again, different temperatures in Celsius and in Kelvin. In physics, for example, I'm working personally in low temperature physics, and we study properties of materials at very low temperatures. Very low temperatures in physics means below 100 Kelvin. So how to reach such a low temperature. The most standard and easy way we do it, we use so-called cryogenic liquids. What is the cryogenic liquid? It seems that if you take a gas like oxygen or nitrogen and you manage to liquefy it, convert it to the liquid state, from the gas state to liquid state, the liquid you will obtain will be very cold. The typical temperatures are shown here. Liquid oxygen is minus 183 Celsius, corresponds to 90 Kelvin. Liquid nitrogen, minus 196, 77 Kelvin. Actually, I brought here liquid nitrogen with me, which we produce at Tbilisi State University. We have special equipment for this. And this liquid nitrogen is in this container. Oh, you can see. So, this is in this special container called Duar. It is like a thermos, which keeps, it has double wall to keep this cold. Okay? So, now I will pour this liquid. So, yes, at the end we can do some experiments together. No, drinking is not good because it's the temperature is about minus 200 Celsius. So it will freeze everything. So now at the room temperature it will evaporate because for this liquid, this is like a hot plate now, so it will evaporate. Okay. So you can liquefy every gas like this: hydrogen, argon, neon, and so on. The lowest temperature you can reach by liquefying helium. Helium is a gas, it's a rare gas which is produced, which is mostly you have on the sun, but on the earth you have very small amount of it. And if you liquefy this gas helium, liquid helium has minus 269 Celsius, it means 4 Kelvin. It's very close to zero. But in physics we have a law that you can never reach absolute zero. You can only approach it as much as you want, but you can never reach. This is the law of thermodynamics. Okay. Now, why I tell you about low temperatures? Because the phenomena of superconductivity, which I want to talk today, is observed at low temperatures only. And historically, it was discovered by this gentleman, Heike Kamerlingh-Onnes. He was working at Leiden laboratory in Netherlands, and he was the leader in low temperature physics at that time. He was in 1908. He liquefied helium gas for the first time, so he was able to produce lowest temperature in the world. And he started to make experiments by using this low temperature liquid he obtained. One of the first things he did, he took this metal, which we are talking, and resistivity we know goes down with temperature. So what happens if we cool metal very close to absolute zero? How much resistivity will decrease? There were different models, different theories at that time, but it was necessary to prove experimental. By the way, I should tell you that, like probably also in economics, you have different theories. But this life is a judge, yeah? Reality is a judge which theory is correct. Same is in physics. You can have very nice theory, but if you prove by experiment that it does not correspond to reality, it means this theory is wrong. You have to reject. So experiment is a criteria of truth in natural sciences, also probably in economics. Okay? So Kamerlingh-Onnes took mercury. Mercury, you know, is a liquid at room temperature, but it is actually metal. So if you take it, cool it down, it becomes solid. And he measured the resistivity of mercury by decreasing temperature. Here his original graph. You see here is a resistivity R, and here is the temperature. You see, only portion of low temperature region is shown. At the beginning, he was observing that resistivity goes down with decreasing temperature, as it should be. But suddenly, at some temperature, he observed that the resistivity jumped to 0. Resistivity at some temperature, resistivity disappeared. And it was completely unexpected. Nobody expected this. And Kamerlingh-Onnes repeated this experiments many times, but at the end he came to conclusion this is a true effect. For this discovery, he obtained the Nobel Prize in 1913. And when resistivity drops to 0, it means that you have no resistivity. You have ideal conductor. The conductor where
you mean the absolute zero or very small?
This is a very good question. I will comment about this just quickly. But before this ideal conductivity, Kamerlingh-Onnes called superconductivity. So now we know superconductivity is a conductor without resistance. This is an amazing thing because you see, you can compare with a ball again. You push the ball and it will roll forever. It will never stop. Can you imagine such a thing in reality? Yeah, but it exists. This phenomena exists, and this is an amazing thing. And the question, of course, as you rightly pointed out, what is zero? Zero is usually some abstraction. Yeah. Actually, because you're economists, I can tell you. Once my physics teacher asked me, "What physical quantity can be zero?" And I was thinking a long time. I could not answer because nothing is zero. It can be very small, but not zero. And he said, money can be zero. Unfortunately, sometimes. But okay. And there was a question. Maybe resistivity is very small, but it's not zero. How to check it? And he, Kamerlingh-Onnes, did a very nice experiment. What he did. By the way, the temperature below which the resistivity is disappearing is called critical temperature. Yeah, it's clear. Below this critical temperature, you have superconductor. Above critical temperature, you have normal conductor.
It's different for different metals?
It's different for different metals, yeah. But let's talk about zero. What he did, he took a wire, he made wire out of mercury, and he put current in. And if you take a wire and put current and close the loop, the current will circulate. But normally, this current will stop very quickly because of resistivity. Yes, in normal copper wire, you can have maybe for 1 second or less, then it stops. But if you have no resistivity, this should oscillate. This should move forever. And he checked this with this experiment, and he found for many years he was measuring this current, which was circulating, and it did not change at all. So Kamerlingh-Onnes could not wait for all his life, of course. And he finished the experiment after some year. The conclusion was that current will circulate minimum 10 times 10 years, so 10 billion years. But this is minimum. Maximum nobody knows. So at the moment is a consensus in physics that resistivity is zero. Okay, but nobody knows how small it is. Good. By the way, one of the applications, technical applications of this effect, is energy storage. You know that power stations produce electricity day and night, but in the night you have less consumption. During the day you have more consumption. So it would be nice that you have a surplus of power to conserve it somewhere and use it during the day. But you cannot conserve, unfortunately, electric current. You cannot conserve. So the application of superconductivity, you can make such a giant coil, such a toroidal coil, and you pass this current in and close the loop, and this current will circulate there, And later you can take it back when you want. And such a systems already existed. They called magnetic energy storage systems. And they are used in backup, emergency backup systems when you suddenly need energy. Okay. These are some examples of superconducting cables. So, with one such a filament, we call it filament, it is very small, but it can conduct currents 1,000 times more than you have now with normal copper cables, because resistivity is zero. In principle, you can pass any current and it will not warm up. Okay?
Why it will not warm up?
Because resistivity is zero, so electrons do not lose energy. They do not collide with anything, so this will not warm up.
What's the price of it?
Okay, we will come to this also. Yes?
So theoretically, if you have a transmission line made of mercury, you can transmit electricity without losses.
Yes, exactly. This is the point. But what is the problem? Problem is that all this happens at very low temperatures. You cannot use it in everyday life easily. To cool it down, it also needs energy and costs. So physicists, starting from the discovery of carbon and gonest physics, started to look for other materials which would be possible to apply at higher temperatures, and hopefully one day at room temperature you can have material which will be superconducting at room temperature. You didn't need to cool it. Then this will be the revolution, technical revolution. I should say in advance that such a material doesn't exist at the moment, but we are searching for it. Okay. So this is the historically how the critical current is changing with years. So this is the mercury, which discovered Camelie-Gonest. Later they found that, for example, if you had lead or other metal like niobium, they have higher critical temperature, and then physicists start to combine 2-3 different elements to produce new alloys, new compounds, new materials with higher critical current. And you see there was some progress. It went up, and in 70s there was a record in this compound was 23 Kelvin was critical temperature. So from 4 Kelvin it went up to 23 Kelvin, but it is still low. And there was, for a long time, there was no progress, and some physicists came to conclusion that probably that's it. You cannot have in the nature superconductivity higher than 23 Kelvin. But in '86, there was made a tremendous new discovery. Two scientists from Zurich, IBM laboratory in Zurich, Professor Alex Müller and Georg Bednorz, discovered new type of materials with very complicated structure, chemical formulas, doesn't matter, which had critical temperatures much higher than all other superconductors before. And you see that in this class of materials, these are these white triangles, critical temperature shoots up almost vertically, yeah, in a very short time. And now the record is 160 Kelvin compared with 4 Kelvin. Still, it is a low temperature. 160 Kelvin means 110 minus Celsius, but it is still a very big advantage. And for this discovery, they were awarded Nobel Prize in '87, and I had the pleasure to work for many years together with Professor Müller at the University of Zurich, and we still continue collaboration. This class of materials here are called now high temperature superconductors. This class of superconductors is called low temperature superconductors. For you it's both low, but for us it's low and high. Okay? And the dream is, of course, to reach room temperature superconductivity. But this discovery showed that the skepticism which existed before, that you cannot find such superconductors, is not justified. So there is now nobody can say it is not possible. But who will discover and when? Nobody knows. Research is ongoing in the world. Okay. But already these superconductors, high-temperature superconductors, are very important. Why? Because they can be cooled down not by liquid helium, but by liquid nitrogen, which I have here. I will show some experiments at the end with these superconductors. Because, and why this is important? Because you are economists, so you should know the costs are important. Liquid helium is a very rare gas, and 1 liter of liquid helium costs about $10. And its price is increasing every year because of the limited amount on the Earth. But nitrogen is 70% of our atmosphere is nitrogen. So it's very cheap. It's about 10 cents, so 100 times cheaper. So to cool down superconductor with nitrogen is much cheaper. And this opens much more applications which are possible. Already they are made cables from these new high-temperature superconductors in Japan, in United States, in Korea, not in North Korea, but in South Korea. So they put these cables in the normal network, electric network, and they check how it's working. This is completely new technology, so it has to be checked in the reality how this will work. There are already filters for the mobile communications because you need many channels in mobile communications, and you have a very good filters. Superconducting filters allow this, and commercially these filters are available, and this equipment is sold. So now, as you noticed, I switched to technical, practical applications of superconductivity. It's this amazing phenomena, but you can ask what it is good for me. Yes. At the moment. If you make electric engines out of superconducting cables, you can have a big difference. For example, here it is shown the ship engine, electric engine, 36 megawatt, and same engine, same power with superconducting cables, each much smaller and much less weight. So this is very important for the ships and submarines. And Siemens and other companies are now working and producing such motors. One of the most broad application of superconductors is producing high magnetic fields. Why high magnetic fields? How we can produce magnetic field? You know, probably remember from the school. You can take a wire, make a coil, and you pass a current, and then through this coil you will have magnetic field. Larger current you pass, you have larger magnetic field. But with normal cables, you have a limit. You cannot pass large current because it will melt. And superconductors are ideal for this because they have no resistivity. Why we need high magnetic fields? I will show now the application in medicine. This is the magnetic resonance imaging system, MRI. Probably you know this or you heard about this. You have in Georgia also, fortunately, we have now many MRI systems. Why MRI is good is because, in contrast to X-ray imaging, it can image every part of the human body, every tissue, which are not visible for X-rays. And you can produce very detailed picture of brain and other parts of the human body. Now, the magnetic resonance imaging is the standard of medicine. Without it, you cannot imagine modern medicine. But the principle of this MRI system is that patient is put here in this hole. It's absolutely painless thing. You just lay there, and they make picture. And inside you, the principle is that you should have a very high magnetic field. And to produce this magnetic field, the superconducting cables are used. So now I show this this system. You see this cable here, it's superconducting system. Inside you have a helium, liquid helium bath. These cables are cooled in this liquid helium bath, and you pass a current and close the loop, and it will rotate forever. You don't need additional input of energy. And without superconductors, such a system would not be possible. With normal copper cable, you cannot create magnetic field. You cannot pass current enough. So this is at the moment largest market for superconductors, MRI system. But as I say, the liquid helium they use at the moment is a very expensive thing. So the next step is now Japanese are working on this, that to use high temperature superconducting cables and cool it with liquid nitrogen. So this will make these systems much, much cheaper and much more available for the people. Okay?
So it can work for ages, yeah?
Yes, until it is cold, but it evaporates, this liquid helium evaporates, and you have to pour again. So in Georgia, they import it from Dubai or from Turkey, this liquid helium. But you don't need to pour it very often, once or twice per year. But until it is cold, it can work forever. Okay. You probably heard about Large Hadron Collider in CERN in Geneva, near Geneva, where they have large accelerator, and then they also produce very high magnetic fields, which are superconducting magnets, and you have 1,232 magnets on the perimeter, which is a 27-kilometer tunnel, 100 meter under the ground. And you have 1,500 tons of superconducting cables in total. So this collider would not also work without phenomena of superconductivity. Okay, but superconductor has another amazing property. Not only zero resistivity, but it has also so-called Meissner effect. What is Meissner effect? It means that if you have a magnetic field and you have material, let's say in this room we have magnetic field, and you have some metal. Now, in normal metals, this magnetic field penetrates completely. It goes through. But in superconductor, it seems that this magnetic field is expelled from superconductor. So inside of superconductor, magnetic field will not penetrate. It will be always expelled, and it is called Meissner effect. And this gives an amazing phenomena which is called levitation. What is levitation? Let's say this is a superconductor, and this is a magnet. So because magnetic field is expelled from superconductor, magnet is repelled. Magnet is repelled by superconductor. So you can have a situation when the magnet is flying over the superconductor, and it is called levitation. Now I will show a small video about the levitation effect. And then we will, at the end of the lecture, we will also see it in reality.
Question before that?
Yes.
There is a big talk about the electric cars now. So do they use the same superconductors in the car engines? Electric cars?
Not yet. Not yet, because the problem of cooling. Yeah, you need to cool it. Okay, so what you see is that this is a superconductor, this is magnet. Until it is warm, it is not superconducting, and nothing unusual. But now they cool it with liquid nitrogen, which I showed you, and now you will see what happens. So magnet is repelled by superconductor, and so it flies.
But it also oscillates between something, right? It also moves around.
The more and less.
No, it is a stable situation.
Yeah, but it does stand like this. It moves around.
No, it doesn't. It not necessarily. If you push it, it will circulate. You will see now. See, you can put it in any position. Every position is stable. This is also very interesting about levitation. Okay.
Is it only with magnets? Like, can we do it with people?
No.
Inside of
Not yet.
If they are magnetic people, yes. Now he removed it from the bath. It will warm up, and this effect will disappear. Okay. So with room temperature superconductor, you would have this effect without cooling. Now this is not only for play. As you said, in Japan, they already have a train which is actually levitating, doesn't touch the ground, and this is made out of superconductor. And this, we have another video about such a
Do they use helium or which kind?
helium. They use helium. Because this technology of high temperature superconductors is not so mature yet to apply, because this is a relatively new discovery. People now learning how to produce good cables with this. And it will come, but in about 5 or 10 years it will be ready. But at the moment they use low temperature superconductors because it's much easier to produce wires, superconducting wires.
Sorry. If you find the superconductors that works at the room temperature, are we going to have a free energy?
Not free.
Because we have magnetic field, and with this magnetic field we can get some energy.
No. With magnetic you cannot get energy.
You
You have to produce this once, then you have magnetic field, but you have to produce it.
Once I will produce,
Yes.
Once you buy the energy.
Yeah, but magnetic field itself is not producing any energy.
but
You're
if we
using it
move
afterwards,
something-
right?
If you move something through magnet, yes, but you have to move it, so it means you need energy to move. Yeah.
But once I move, the light will be always on, right?
Yes. No, because if it's circulating, but if you need to bring it to the for example, your computer, then the energy will be spent. Yeah. So this is not free energy. This is just reducing loss of energy, unnecessary loss from the power station to the consumer. These cables, you lose energy on the way. It is about 25%. Yeah?
You can also use the energy generated in some.
Yeah. Okay. Until this is being set up, this video, I suggest to start with the experiment, and later we can see video. Okay. If you agree. But before, if you have some questions, you can ask me.
I would
Yes.
like to hear some comments about gold. Gold has conductivity, but
Gold has a good conductivity, even better than copper, but it is still not zero. And gold is actually practically never becoming superconductor, so it's not so useful.
but they use it in cosmos, right? For better conductivity.
Yes. But now in the cosmos you can use even superconductor because it's so cold there, so you can use superconductors.
In energy transmission systems, now is a big trend of developing high voltage direct currents that they're putting in the North Sea, for example, to connect.
Yeah.
Is superconductivity somehow involved in that?
Yes, exactly.
Can you
because
comment on that?
for the direct current is ideal, superconductors are ideal, because direct currents can pass with zero resistivity. And there are big projects. I even heard a project
From
about
Norway
Sahara.
to Britain.
Yeah, from Norway I did not know, but I know about project that to put, for example, solar panels in Sahara when you have a lot of sun, and produce energy there, and with superconducting cables bring it to the Europe.
Yes, there are such projects, but right now, like Norway is developing the connection to United Kingdom through the high voltage direct current cable.
Yeah. So I would say that this technology is a technology of the future, but it's already started to be used, and you will hear more and more in the future. That's why I wanted to inform you about this, and because also effect is very, very unusual, because as I said, a zero resistivity you cannot imagine, like zero friction. It doesn't exist in normal life, but this is we call it the quantum phenomena. The quantum phenomena in physics is that you cannot imagine. You cannot imagine it, but it exists. Okay. So this is the strain, yeah, superconducting strain. This is This is a track from Tokyo to Osaka. This train circulates between the Tokyo and Osaka, and it reaches velocity up to 500 kilometers per hour. Because it does not touch ground, it can fly practically. This is this track here. This train also has normal wheels. At the beginning it stands on the wheels, but after it accelerates, the wheels go in and like in the airplane, so and then it flies. Yeah, we will see indication of the speed of this train. Now train takes acceleration, and you will see. It can go even faster, 550, but normally they stop at 500. So this is the, you can get impression, yeah, about it. Now it comes back slowly. Okay, that's it. Okay, this is because you are economists. I prepared such a slide. The world market for superconductivity, yes, in billion of euro. So, as a function of the years, you see it's increasing. What is interesting that this segment of this color shows that MRI imaging segment is most used in the world now at the moment. Is most sold, and but other segments are also becoming more and more. For example, new large-scale applications. This is red, and there is also low-temperature superconductor, high-temperature superconductor. Is shown here, and this is the fraction of high-temperature superconductors, which takes market. It's also, you see, it's increasing with the years. So when it develops the cable production, it develops a technology and becomes cheaper and cheaper and more, of course, then it is more widely used. But if new superconductors are discovered, and this can happen every year, then new applications will be possible, and this situation could explode overnight. And that's why we physicists are working to search for new materials and to understand also mechanism of superconductivity, because this I did not mention, that this mechanism of high temperature superconductivity, it was discovered in '87, but still we don't know why they are superconducting at such a high temperature. This is one of the most important open problems in modern physics, and me and my colleagues are also try to work and understand this puzzle. And with this I would like to thank for your attention. And now we can do experiments together. You can see it, for example, here inside I have small magnet, and see, it's hanging, so this is really a magnet. But if you bring it close to superconductor, nothing happens. So for this, we need to cool it below the critical temperature. And
what's the material of this superconductor?
this is this consists of 5 different elements.
The one we saw with high
So it's
Yeah,
high temperature.
yeah, high temperature superconductor.
H3PO.
This is yttrium. Those who know chemistry, yttrium, barium, copper, oxygen. Four elements. Alloy out of 4 elements. So now I will put it here and we'll cool it down by pouring liquid nitrogen.
איך המגניט הזה?
כמעט תכינו לי. Šali tinu likvida.
How come it's this?
Maga tu se sak marisia, იმიტომ რომ მაგაც ძალიან დავალი ტემპერატურა არ ჭირდება. ნაყინის შესანახად. So let's try now again with these magnets. What will happen? Nothing happens. It means it is not cold enough. I will use this. You can touch, but you should do it quickly because you can freeze finger if you do it.
You can touch if you want, guys. You can touch, but no, it's just careful. Careful. Be careful.
Can I put my hand inside?
Very quickly, yeah. Okay, so now I put some spacer to fix the height. This is just a normal thing, and I will put this magnet over it. So now when I try to put this magnet now, I see I have resistivity, you see? It's repelling. It's very difficult to put it on. Yeah? I will show now different method, but let's try by force. Yes? So. Now this is in the air. Yes? So, And it is in a very strange position now. You see, usually you expect it will fall down.
Yeah.
But I can, it rotates. So now I can spin it up.
It will rotate infinitely, yes, if it stays
Yes,
cold.
yes, yes.
Did somebody try?
Actually, Boeing is making experiments now. It's making that they make such a, it's called a flywheel. So you have superconducting heavy thing, and on superconducting based on superconductor, it can rotate without friction, yeah, between two things, and then it means that you save mechanical energy. You know? Once you rotate it, it rotates forever, and this is also saving energy.
It then rotates.
Now I will remove it from the.
It's not cold. It will burn.
But if
It's warm already.
Oh no, you can try longer.
if you try longer, it will burn.
Okay. Now what I will do to observe levitation, I will make different experiments. The superconductors have memory effect. So if you fix the magnet on some height in the beginning, after cooling it to superconducting state, this will stay on the same height afterwards. So now you see this is a spacer and this is a magnet. I will put even more distance. See? So now I will cool it together. I will cool magnet and superconductor together, and later we'll remove this spacer. And then you will have more stable levitation. We call it field cooling. We cool it. So now it cools. Tam boxan. Onu WhatsApp-ը կարողա կացուես։ I think it's ready. Now how to remove it? It's really cold. Okay. Now I will remove this one. You can try to push on it. Daha ჭირეთ ხელი.
Minimum დააჭირეთ.
კაიო, დააჭირე, გეწვის.
შავის არ წვდება.
არა,
просто ის სითხეა დანახარჯი.
ხო, სითხე.
ეს სითხე მე რა გვეკეთებ?
გამომწვით.
To make it more visible, I will remove it now from this bed. Now we can do one more experiment. Now I put magnet in. Now I put magnet here, and I will try that this flies over this.
პრინციპში რატო თით სადაც და
ეხლა ჩვენ რო დიდი რაღაც დაგვიდა შუაში მაგას დარჩებოდა ხო ის?
ეხლა იქნება იუ.
So let's try.
მე.
აზოტია ხო?
Აზოტია. Nitrogen.
ეს აზოტია.
აზოტია.
აუ რა მაგარი.
Yeah. For in cosmetology, they remove some defects on the skin. They freeze it. So how it is produced, the nitrogen? Somebody asked. Yeah, it is produced like you in principle, like you have refrigerator at home. What refrigerator makes at home? You have compressor, and you have a liquid freon is moving inside. The gas is actually gas. When a compressor presses this gas, and then this gas goes to the expander, it expands suddenly. And in physics, if something gas expands quickly, it cools down. So this cycle is repeated. So compression, expansion, with this temperature goes down. This is the same principle we have by producing, but you need much larger pressures and much more powerful compressors. But principle is the same. We bought recently this the machine producing liquid nitrogen. This American company Cryomech. It is not cheap. It's about $200,000 costs, but then you can operate it for years. And we need this. Also, chemists, biologists, medical people all need the liquid nitrogen. So everybody can use this now in university. Okay. So now let's hope it is cold enough. I think it is. And I will remove this spacer. And now you can spin it. So this is the flywheel. So as I said, Boeing and other companies produce very heavy thing which is rotating. So when heavy body is rotating, it has energy, kinetic energy. And this is the also way to save mechanical energy. So if somebody will discover room temperature superconductor, it will get Nobel Prize for sure.
When is the deadline?
Okay, so now you know what is superconductor is?
Yes.
Thank you very much.